Today's lecture is going to be about transform, and we'll start by a quick review of our first two lectures. First lecture, we looked at image, and then we look at how you could turn the image array into an image matrix. It's one way to represent images just simply by the raw pixels values it has. So we looked at, well, we have a 1D array, then we could break it down into width of 5. So we could have this first row will be here, the second row will be here, and third row will be like this, and so on with width of 5. And so just to as a practice, with this field, the second row, we have first row down already, 1, 3, 4, 5, 1. The second row will be 4, 2, 4, 5, 6. All right. And so one thing we can ask ourselves is that what is the dimensionality of this representation if we represent by raw pixels? So we need one dimension to hold one value in this case. So for a 5 by 5 image, in this case, 5 by 5 image, we need 25 values, 25 dimension to represent this image. Okay, so as you can see, as image goes up in resolution, this dimensionality is going to grow quadratically, and it could be really big. So, and then in the second lecture, we look at function. We can represent an image using a function. For instance, we looked at this. We define a function as a 2D, image as a 2D function with x and y, so x plus 1. So we looked at how you can fill up this coordinate. So we have all the value filled out already with only 4 as a quick review. So this value is going to be 1 plus 1, so 2. And this value going to be 2 plus 1 is 3. And this value is going to be 1 plus 2 is 3. And this value is going to be 2 plus 2 is 4. So we look at these 4 values. And again, going back to the same question, let's analyze the dimensionality of this representation. How many dimensions? So if we define this image as a function, and this could be rewritten as a times x and plus b times y. So in fact, the coefficient a and b is just a equals 1 and b equals 1. So we use only 2 values to represent this function. And so this dimensionality is 2. And you could see that we can go from 25 to 2. So a lot of this computer vision algorithm really about to find the underlying function that we could use much lower dimensionality to represent the image. Also to be able to perform tasks like recognition and in order to get meaning out of the image. In this case, another interesting property of defining image function is that even though I show you a 5 by 5 example, if we have a 100 by 100 example, higher resolution, we still use exactly 2 numbers to represent the image. So with image, we can define the value everywhere in the 2D space, and then that could be extended to 3D as well. And today we're gonna look at the third representation that we're going to represent by point, somewhere in between, not like a function, but a set of point. And that is, so for instance, perhaps if we have an image of the face, and then we have all the pixels about the face, which is number 1, or we can have a function, some kind of function with lots of parameters to generate this image. That's our option number 2. And today we can also look at option number 3 is that we use point. Suppose we have just this 4 point, eyes and also the shoulder, 4 point to represent. But in this case, just say we have 3 points. And then this image was reduced to the point we want to pay attention to. And there's a phrase called interest point that we use a lot in computer vision. So in this case, it's trying to plot A. What is A? A is 2 and 1, which is 2 and 1 here. So this is where our A is. Okay? And then where is our B? B is going to be 1 minus 2. 1 minus 2 is here. So this is where B is. And then where is our C? C is minus 1 and 2. So minus 1 and 2 is here, C. And once we have this 3 point, so we could kind of infer, oh, maybe is describing a triangle. All right. So this is a third way to represent images based on a set of points and their locations. So once we have these 3 points, so today is about, well, if we have this 3 point, what if we have this triangle move to the right, move to the left, or rotates? We would like to have a system to analyze this shape of this triangle that we could be able to say, oh, they are actually the same. and to be able to analyze how the things move around a rigid object like a triangle, like a mouse, like the pen I'm holding in my hand, that on my head, if I move left and right, up and down, get closer, look bigger or smaller, it's the same face. So, all right. So it's important to understand how a set of points transform, how a group of points transform in a space that would like to be able to relate them. So the first transform we're gonna look at is translation. So translation, we could describe as use this function translate, and typically takes two parameters: the displacement in x, t, say t of x and t of y. So there's two parameters. So say if we have t x equals 1, t y equals 2, then how we could, so then we have a set of point a, b, c again, then I'll replot it here. How does it take for us to translate these 3 points? So the equation we're going to be, we have x, it will start with x, y, x and y. Then we'd like to convert, transform by translation to x prime and y prime. So this, the equation is quite, okay, as you can expect. I will want to add the ty to x and then assign to our new x prime. And similarly for y, we'd like to add t of y to y prime and realize I make a mistake. In fact, this is tx. T plus tx, then get our new x prime. Y plus ty and get y prime. And we'll compute this. Minus 1 plus 1 is 0, and 2 plus 2 is 4. Okay, so 2 plus 1 is 3, 1 plus 2 is 3, and 3 plus 1 is 4, 2 plus 2 is 4. Okay, all right. So in this case, we just add number, add this displacement in it, and then we're gonna draw the new location again. So for A, we move to the 1 to the right. For Y, we move 2 to the top. So this is our A prime, and this location is 0, 4. Does it make 0, 4? Does it match the calculation we did? Yes, we just did the same calculation. So this A prime, and for B, follow a similar pattern to the right, and so this is our B prime. For C, is going to be this way, also C prime. And if we draw this triangle, so we have this shape, and after the translation, we get the same shape, but just move to a different place. With this system, then we'll be able to say that, oh, they are actually the same shape. They are related to each other through a translation of 1 and 2. Let's analyze the next case, a very common transformation called scaling, and scale. And so we have, just this time we have 2 parameters as well in 2D. One is a scaling factor along the x dimension, s of x, s sub x, and s sub y is the scaling factor along the y dimension. So let's use a concrete number as an example. So suppose the scaling factor of s sub x is 2 and s sub y is 0.5. And the computation we want to do is that we would like to assign sx times x to be our x prime and sy times y to be our x prime. That's our goal. Then we actually calculate this, and minus 1 becomes minus 2, 2 becomes 1, and 2 becomes 4, and this 4 becomes 2. And then we will plot this. So the way we can plot this is that, so, and this scaling is actually relative to 0, which is here. So it's important to analyze in this way. And for x, we started from here, and it got twice as big. So kind of ended up twice as big. Or how do you say twice as big? Actually, I beg, so for x, it's going to be twice as big and end up here, okay? And for along the x, and for y, it's actually becomes smaller. Kind of actually, it's actually, that's not kind of ugly, so it becomes like this. So this is should be, and if we read all this, and then we have a new location, which is here, A prime. All right, and for B, let's maybe use a different color. So this is here, and we have X and Y, and for X become twice as big, so kind of ended up here. For Y, it's kind of half of this, is kind of around here, and then we looked at it together. So it's here, And so there's a new location of B prime. And so the thing just like it becomes smaller. Let's just draw. Does it make sense? Will they look smaller? So we have A and B here. And after the scaling becomes kind of like this, okay, for this line. So that is scaling. That's what we want to accomplish with this equation. And so for the rest of the lecture, we're gonna just get into linear algebra, matrix multiplication, a core of lots of this calculation we're gonna do for the rest of semester. And this is a prerequisite. So assuming that you have taken linear algebra, and this is a quick refresher. And so, but also like to teach you my unique approach to matrix multiplication. You might not have learned this or seen in other places. So first, I would like to show you how I will calculate a matrix multiplication. It's supposed to have a 2x2 matrix over here. Then let's use a different color. So we also have a 2x3 matrix here. Typically, when you do math or do the algebra, they like to write things like this: A, B, C, D times x1, y1, x2, y2, x3, y3, and then good luck for you to remember all the different rules for you to get these 6 numbers. Okay, so the way I like to multiply matrices is that I move the section matrices kind of up top a little bit and create this sort of offset formation, and that give us lots of these advantages that you could multiply and then see how the rows and columns, how each component should be multiplying and added together. And let me show you what I meant by that. So let's consider this. We can see with row vector R1 and row vector R2. And for my P, the other matrix will use P to represent 3 points, P1, P2, P3, with two X1, X and Y1, XY coordinate. So we have this column vector here, and column vector here, P3, P1, P2. And then with this kind of arrangement, what we can the way that we can analyze is that each cell basically just a dot product between this row and column vector. In this case, it's very easy for you to visualize the correspondences. That for this one, let's just erase this so you can see this. So this one is going to be R1 dot P1 just because how the two intersect. Okay, all right, and then this is going to be R1 dot P2, R1 dot P3. Basically, you could just take a look at how they intersect, and you'll be able to determine which are the two vectors that you should be dock them together. Okay, in this case, it's quite cleaner this way. And similarly, for the second row is dot R2 dot P1, R2 dot P2, and R2 dot P3. Can easily lay it out. You don't have to remember that hard how this corresponds. In the more common representation on the top, unless you just took linear algebra like yesterday, you might remember this. This is the correspondence. But if you didn't, you've revisited this, you never multiplied matrices for like a couple years, it came back, you have no idea. You cannot remember. But with this representation, because of visualization, the way that you can see how they intersect, you could always remember. They provide this visual cue for you to remember how rows and column vectors should correspond in order to derive a new value in your output matrix. In this case, now we're going to move on to see how things break down into the individual component within each vector. So for instance, for this one, R1.P1, what is it? So it's going to be A times x1 plus B times y1. And so there's another visual trick I like to use to remember that is that if I want to derive this one again, this is how things should match. And I will take this one and just draw over here. And I get A x1, and if we do this one, and I get B times y1. So this is how I will visualize this. And then this just basically take a sum of these two, and I can derive this A x1 plus B y1. So this is how to derive this the value, calculate the value of this particular location. And now maybe use a different color and to show you another location. So suppose you want to calculate this location, okay? This location. How do you remember what other values and components are involved? So the way is that I'm going to see, all right, this is actually here, okay? This is actually here. This is how we intersect. So I know exactly this is a row and this is a column that I should be consider. All right, now once I decide that, I can do this similar match. This one, C matches here to X2, and D matches here to Y2. And so I'll write C times X2 plus D times Y2. Okay, so that is how you multiply that particular element. So I can do just one more time real quick. I can follow. So I can just eyeball this. So this one going to be A X3 because I can just like kind of eyeball this. You can see my hand in the upper right corner of this camera. So Y3, I can eyeball Y3 going to match in B. So BY3. And I can do the same thing now down. Down here I have C X3 plus dy3. Okay, so this is, you take some practices, but so you have a worksheet that you got today to practice this, and this might be a new way for you to multiply matrices you've never seen before, but you'll get the hang of it very quickly, and hopefully you appreciate it. And we're gonna use this like all the time throughout the semester. Then you'll be surprised how good you are in terms of multiplying matrices by the end of the semester. All right, okay. Now let's extend this example to a 3x3 times 3x3 matrices example. I'm going to, so first I can look at the dot product. Now I can see A dot Py, A dot P2, and A dot P3 very quickly, just because I know A and P1, P2, P3 that correspond. And then for second row, P, I can do even quicker now. So I'm gonna just write it out as fast as possible. Hopefully you can see that I don't have to remember too much, just because I have this visual cue of the correspondences between rows and columns. And we'll see this for a lot throughout semester in cross entropy computation, in self-attention matrices. We're gonna see all this, and even in the clique model for the multimodal the multimodal shared embedding, we're gonna see all these matrices in multiplying this way. And then let's just consider individual component right now. I don't have time to do all of them, but I'm just gonna do, again, just do this location. See, remember how we can do it? So can eyeball. So it's going to A1 times X1 plus A2 times Y1 plus A3 times Z1. Okay. All right, just because these correspondences. And you can quickly do another one. Say I do this one instead. So now can eyeball. So all gonna be these three things. And then also these three things, these correspond. These are the correspondences, how they intersect. So now having established that, I can write out B1 X3 plus B2 Y3 plus B3 Z3. Okay. All right, and you can do the rest if you want to, but not. And so that is at the kind of symbolic level, how algebraic level, how we sort of the way that we could reinterpret matrix multiplication using this formation. It will be really useful. Again, you do a lot, but for now, this is the first one I'm gonna do with the real numbers. So I have this number laid out, and you can see that how can we calculate each one. So for the first one, it's going to be, now can eyeball 3, we're gonna remember this, right? So it's going to be 3 plus 4 equals 7. Now I'm not draw a line here, just kind of match by hand. 1 and 10, right? 1 plus 10. So let's say I 10 because 2 times 5 equals 11. We're gonna do this, okay, 2 and minus 2. 2 minus 2 equals 0, okay? Now I finish first row. Second row, 3 and minus 1, 2 and 1. It's going to be 3 minus 3. Plus 2 equals minus 1. Now I have 1 and minus 1 is minus 1. 5 and 5 is 5. So we have 4. And 2 and minus 1, what is it? Minus 2. Minus 1 and 1, what's that? Minus 1 is minus 3. Hopefully that's correct. And so I have this kind of cheat a little bit. I want to verify, so I'm going to use the equation M mult. And now I'm going to select this. And then for first select matrix and also select this and then see whether I get the same number. Yeah, 7, 11, 0, -1, -4, -3. Yes, yes, happy. Okay, all right. So now having done matrix multiplication using this formation, so we're going to apply matrix multiplication to the translation task. The trick for to express a translation is to in matrix multiplication is to add a little one like this. Okay, and then with that we kind of do, so we have this translate t1 tx ty. So the translation matrix, the format I'm gonna show you is going to be one, start with a kind of identity matrix, sort of like shape, but then for this location I'm gonna put tx and ty. And then so magically if you multiply these two and you get this, and you will have arrived the same equation we looked at earlier for translation. And let me just show you how it works, okay? So x prime, so remember we did, now just calculate the first row, so is this and this and this. So 1 times x plus 0 times y plus tx times y. What is this? So this is x plus tx, which is the same equation we looked at it earlier. Then we similarly do this one, but we're gonna match again. So now we're gonna match this. I realize it's very hard to see. Can use a different color, blue, this and this and this, okay? So we're gonna have 0 times x plus 1 times y time plus. Actually, I realized I make a mistake here. This should be plus, okay? And ty times 1, so which give us y plus ty, all right? So now I just prove the equation that normally could derive how that transformation matrix multiplication actually give you the same result as applying just translation to each component. So we can do the same thing for scale matrix. So scale matrix, so we would like to have something that looks like an identity matrix, but instead of the filling R1 for the diagonal, we'll simply put Sx and Sy along the diagonal. And we add a little one here, augment our xy 2D coordinate with a little one, and then we can get this form. And to show that we could do that, we're gonna do one more time. I'm not gonna draw the line, but just gonna eyeballs s and y, sx and x kind of match, and 0 and y, right? Plus 0 times y, 0 and 1 times 0 plus 0 times 1, and as a result is x times x, all right? And for this one, we're gonna do x 0 and x, x1 and y is y times y plus 0 and 1, 0, 1. And so this is 0 out, 0. The left with s sub y and y. So we can scroll up, you can realize we derive exactly the same equation that we saw earlier for translate and scale. But now we have this kind of nice and neat matrix multiplication form. It's at this point you might not appreciate why do we kind of go through all the trouble to do matrix multiplication. But as you see more, you're gonna see why in a second. And then another thing which is kind of nice about this representation is that you can actually combine a scaling operation followed, this is very important, followed by translate. This sequence is very important, scale and translate. So you put it together. Remember, we add these two matrices together in this way, kind of take a union of the two. And this particular matrix will be able to perform scaling and translation at the same time. One matrix multiplication perform two things at the same, two transformation. So that if you can see whether we can write it up. So this sx and x, all right? Sx times x plus 0 times y plus, I'm gonna just eyeball. I think I see enough of this. I don't have to, I can do a bit faster. So I can sx times x plus tx, okay? So scale x and add the translation of x. Does it make sense? All right. So now the next one, 0 times x plus s sub y times y plus t1 times y, and this gives you s1 s sub y times y plus t sub y, okay? Similarly, scaling y and add translation along y. So that is how the scale and translation matrix can be combined together. And then with this transformation expressed as matrix multiplication, you can very easy to stack them up in this way. So for instance, we like to scale by 2 to 3 and then translate by 2 to 1 and then scale and translate and kind of together. So first you need to learn. Now we can apply 2, 3 to this formula. So this is actually the exercise you will do this week. So basically, given a scale 2, 3, can you write the translation scale matrix? So it's going to be 2, 3, 1 along diagonal. Everything else is 0. Okay. All right. So scaling and translate. What is 2, 1? So 2 translate going to put it in this location, but we have an extra 1. But everything is 0. A diagonal 1. So this you can always translate no scaling 1, 1 is no scaling, right? It's another way to interpret the translation matrix. And lastly, so you have scale and together, basically put them together. All right. Okay. So, and then in order to apply this 3 transformation to our input point 3, 2, let's add 1 into it. And then we just calculate this matrix transformation. Now first, I have M1. This is this G. So this is going to be my M1 times G, okay? But you can now I can do it real quick, that's 6, because of 0, 0, very easy. So 3, 0, 2, 3, 6, and it's 1. So you can do the other way, the same thing. 3 times 2 is 6, and 2 times 3 is 6. 61. And then multiply this again, we get A71. Okay? And just do it very quickly. And then the last one, do the last one nicely. A times minus 2 is minus 16. 7 times 0 is nothing. And 1 times 2 is 2. Okay? So this minus 14. Okay, and next one, 7 times 0, nothing. 8 times 0, nothing. 7 times minus 1 is minus 7. 1 times 1 is 1. So it's minus 6, and this is 1. So this is how I will calculate 3 transformation using 3 matrix multiplication. So we'll revisit this in a little bit. But now we're going to talk about a slightly harder transformation, is rotation. And rotation transformation given as theta, say I just use T to represent theta. Is a degree we like to translate. And then the formula for this rotation matrix is going to be cosine. We're not going to derive this in this class, but just give it to you. Minus sine of t, and this is 0, 0, 1. And then here is a sine t and cosine. Okay, so this is you're going to achieve the translation of this xy, and you get x prime, y prime, that with respect to 0, the origin. And so if you multiply this out together, and you will see this going to be cosine t times x minus sine, you might seen this in your kind of polar coordinate in the calculus earlier in your undergrad, or for seniors, you are first or second year, I guess. Anyway, so this is, as a practice, I'm going to just multiply this out. So this is something that what it looks like. You kind of remember seeing this kind of form before in the past. And let's do this one with real number. So rotate 90 degree, phi 2, rotate 90 degree, what is it? So let's look up 90 degrees here. I have a very, very simple trigonometry table. For 90 degree, cosine is this location. And just you can see cosine, sine, minus sine, okay? Cosine is 0, minus sine is minus 1, and this 1 is 0, so quite simple. So when you multiply this out, you're going to see that 5 times 0 is nothing, 2 times minus is minus 2, okay, and then 5 and 1. So you can see that what happened. With 90 degree, you flip xy, but one of them become negative. So it's kind of like that. If you draw this, that makes sense. and then rotate 30 degrees. Then minus 2, 5, 1, rotate by 30 degrees. We can do similar looked up. So this is going to be cosine 30 degrees. Gonna look at maybe just a different color now. So 30. So this is going to be cosine, right? So square root of 3 over 2. So I can copy over here because they are the same. But this is going to be minus cosine. Minus sign is 1 over 2. 1 over 2, 0, 0, 0, 0. And then we can do the multiplication. What is this value? Minus 2. So we're going to just kind of write out nicely. I'm not going to, so like this. Plus 5, plus minus 2. Actually, minus 1 over 2. Minus 1 over 2. Minus 1 minus 2. 5. Okay. And this is going to be 1 over 2 minus 2 plus. So I'm just doing this as a practice of being able to eyeball to match my rows and columns correctly and 1. So you never really have to do this in practice. It's more like as learning how the rotation matrix work. Okay, so we're gonna write code in the next tab so you can see how that work in action. So now I'm going to do is to show one mathematical property of maximum multiplication. You might remember that your professor told you that maximum multiplication is associative. What does it really mean? It means that you could multiply matrices in the suppose your sequence multiplication, you can multiply any part of it first in any order you want. And that has an implication of how we could apply transformation efficiently. And you can see what I'm saying. So we just did this part by hand, okay? So this, but I'm going to write out equation. So what is this? Suppose we have a group of points, but that's one point, right? Just go G, and this is my 3 matrices for transformation. And so this one is going to be M minus G, okay? And then we multiply this thing with M2, okay? M2 times the result of M1 times G multiplied by G. Okay, and then at the end, this is this thing, and multiply with M3 is M3. So this the parentheses imply the order of the multiplication. So this is like what we did earlier, kind of it just following the right sequence. But then turns out with associativity with matrices, you can do is that suppose so we have this M1, M2, M3. So instead of multiplying kind of 1 by 1, what if we multiply all this 3 things together and we're gonna get this thing? So what does it work? So we first we have M2 times M1 here. So this, whenever we calculate a couple of values, this is actually 2, 0 to calculate this. And then once I calculate this and multiply this with M3, so I have M3, M2 times M1. So this gives me, what is it? I have 2 rows calculated. Let's say this is minus 2, this is a 0, this is minus 2. And then if we multiply this thing and this thing together now, did you see what's kind of skipping in between? You get the same thing. It's going to be, say, 3 times 4 is minus 12, and 0 and 1 and minus 2 is minus 14. Just proof that they're saying 2 and minus 2, 3, 0, nothing, 2 minus 3 is minus 6, and 1, 0, nothing. So minus 6, 1. You can see they are exactly the same. All right. But what is different is that in terms of the order operation, we have this combined matrix, okay? And then times G. So we pre-multiply these 3 matrices, and then we multiply our G. So there's an order. And whereas before, we just multiply 1 by 1, kind of like this. So we get the same result. Okay? And the reason why we do this is we can save computation. You can't really see it in this example, but we're going to see it in the next slide. Now we finished all the by hand part. I'm going to take you to the larger example in the Excel example, so you can see that why all the things we learn kind of matters. So first is that I would like to show you a revisit of coding out the maximum multiplication. So earlier we learned that one way to look at it is to take say we have this 6, all these row vectors, say R1, R2, and here we have P1, P2, and blah, blah, blah. And this is going to be R2 times P2, right? So we kind of established that correspondence. So we can use a dot product in the sum product is the way to do dot products in Excel. So you can say sum dot product. So we're gonna select this thing. And then I also want to select this one. But for some dot product to work, they have to have a same orientation. So if I do this, it's going to fail. But what I'm going to do is then I add transpose to my second one, transpose. Okay. And then we'll get this number. And then we're going to erase this so we can actually see the number. All right. So, and then we copy this over then to get suppose a copy over here, they will know that it doesn't quite work because it's shifted. So remember the little trick we have for this. I would like to fix, what is it? What do I want to fix? I want to fix the row. So this 3 to 6, always stir 3 to 6. And for the blue ones, I would like to fix the column, D and G, always D and G. Once I do that, and then I paste over here as a text, you can see that it looks just about right. Just do this one. Looks just about right too. Do this one. Then copy here. Okay, the correspondence is all correct. So now I'm confident that I'm going to select the entire, I copy that, I'm going to paste to entire thing. So now I completed my matrix multiplication. Okay, and one interesting feature that you will probably use a lot is that if we build the formula, you go to the formula tab here, and then you can say there's a tracing function. So we can trace the precedent. Let's do that. You can actually see the arrow of how this particular cell is calculated from these two rows and columns. And do another one here. All right, kind of like this. And it looked really fun. We had multiple layers of this transformation. You can kind of trace back when we get to the multi-layer perceptron neural network. We're gonna see this tracing. It will be pretty fun for you to see, get the intuition of back propagation as we apply this principle to neural net, multi-layer neural net. Let's remove those arrows. And so we're doing the hard way in order to see rows and column correspondence. But in practice, once you internalize that knowledge, I will just use the built-in matrix multiplication, M main mult, and just select my first matrix, and then comma, and now I select my second matrix, and parentheses, and I get this whole thing. All right, but let's fix this. I like this to be just with the right width of 4. This is my preferred width for my exercises. Now we just did that matrix multiplication pretty big. I will never do this by hand, but now it's too big to do it by hand. So I'll just use formula. But I did it by hand just because I want to kind of have a better understand better. All right. So now we're gonna look at how we can implement a linear transformation. So we have add some real number to it. So A, B, C, D, these 4 numbers, and then this 4, 2. We like this to become like this. So one way is I can use a formula. Actually, what I do is that I like to just copy away over here. This is my ABCD. Copy this way over here. Okay, earlier I just put the ABCD. I can just write ABCD over here. So this is my ABCD. And then we have X1, X2. I also just actually not copy, reference this too. So I have this. And if we use a formula, like the dot product is going to be this times this plus this. They're doing a dot product in the kind of like in the kind of base hard way, okay? And then I do this similarly, this times this plus this. This is kind of allow you to practice the correspondences. So now I can do this, can review this formula. And I can go back to formula and play with this precedence again. You can see how this value are kind of dependent on each other. Then you can also let me just copy this value, refer to this value again, use the same value. All right. And I'm going to refer to these two values. So I have the same value. Now I can use a different way to represent this. I'm going to use sum product. I'm going to do sum product and for this one, and then I transpose these two, and then I can get a sum product. And I do this again. But this is gets shifted down a little bit. So I'm gonna do reselect this two. How do I do this? Okay, anyway, let me redo this. Sum product of these two and then transpose. Actually, they do transpose first. Transpose of these two. Okay, and they get the same number, right? And lastly, I just do metric modification to accomplish exactly the same thing. Okay, now just put it, use a small number to show you how trying to perform the same calculation using three different way. Now I can do the metric modification. Once you have become familiar with how the dot product correspond to each other, and you can just do a metric multiplication, and then these two, okay. Okay, 1626. I'm pretty happy about the results. All right, so this is formula versus sum products versus math multiplication. Now we're gonna do a translation matrix. What we need to do is that we have to translate x, y, x, y. We have a whole bunch of points instead of just 1 point. We have a whole bunch of points. In order to multiply that using multiplication to solve translate. So first we can figure out this is my matrix, but it's not correct. So this is my T1x and T1. So first of all, I would instead of 0, I just gonna assign this to this one. And this, instead of 0, assign this to this one. So following the equation we looked at in the previous three. So this is my transformation matrix for translate. And in order to use multiplication, first, I have to add this group 1 to each of these 2D points. And there's a technical term called homogeneous coordinate. We're not going to bother talking about this today, but we might talk about it later. And so once we have this set up, the beautiful thing is that now we can do matrix multiplication and then select our translation matrix and select all the point with this one augmented with, and then we can get this new thing. And we have this visualization that didn't work for some reason. Let me see why it's not working. So I have this visualization to show that things can, okay, here, this is blue point. Why is this so hard to see? So I have this blue point here, I selected. All right, now we can kind of play with it. So if I move to 3, you can see, oh yeah, now it's showing. Okay, so you can see that I can just change this different translation matrix, and this shape we're gonna just move around. Okay, now we're gonna do that for translation. Translation is we're going to parameterize these two locations to x sub x and x sub y. So we're going to set this to f sub x, set this to f sub y. And once you do that, I could multiply them, but before I do that, I have to set everything to 1. I add a little extra 1 here. Okay, and then once you do that, I'll be able to multiply this matrix multiplication. Select my scale matrix and my input, a group of points, locations, and then get this one and get it. So now I can see that blue one kind of grow to the top because my y scaling vectors too. So if I shift then to 2, 1, you can see that grow in a different direction. 2, that it go in the kind of like linear. Or just do this one. You can see that the things change. Okay, and now we're gonna look at scale and translate. How we kind of look at them. Remember, we can combine scale and translate at the same time. So now I'm gonna do my set this up, set my transformation matrix correctly to be this. Okay, follow my formula. And the one is already added. Now all I have to do is just add my matrix multiplication formula, multiply my transformation matrix with my input point, and then we can derive the new point. And now I can just change a little bit. Let's scale to 1.2 a little bit. So it can become slightly bigger and translate like this. Translate 1, 1, 2, 2. Actually, no, I got the opposite. Sorry, I need to fix it. So not this. Okay, so this scaling factor is here. No wonder it looks very weird. So scale factor is here. I make a mistake. And translate parameter is here, this location. And then once I set this up, it looks about right. Let me see, is it right? So I change it by 1.5, 1.5, so a little bit bigger, but not too big. 1.1, if I 1.1, it'd be just slightly bigger. Okay, now we could see, create a rotation again. So supposed to be degree, say 45 degree, but for the building formula in Excel that take radian, so to convert to radian, I want to convert 45 by times pi over 180. This is how we convert degrees to radian. And now we have this one. So remember this location, cosine this value, and this cosine this value, the cosine theta, and this is minus sine. Oops. Oops. Okay. Type slowly. Minus sine. Select this. And this will going to be just sine. All right. And those are my rotation matrix. And add 1 to all of them. And then I will just multiply matrices. This is my rotation matrix. And then we have this group matrix like here. Okay. So now I can see the rotation in sort of like operation in operation. It says 0, kind of back to where you are. Rotate a little bit, rotate a little bit, rotate a little bit, rotate a little bit, rotate 45 degree, rotate 90 degree. You can see that it works. At the end of to talk about the multiple matrix transformation here. So in this case, earlier we just have first again 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1. We almost finish. So and then I gonna fill it real quick minus because translate, and this is scale, so 0.5, 1.5. This is rotate. What is it? Equals cosine 45 times pi over 180. Okay, this is the same, and this is going to be minus sine 40 times pi over 180, okay? And this is going to be sine 45 times pi 180, okay? So with this, and then translate phi 2, that's easy. So once I have that, I could have my matrix multiplication of this whole thing, and then this whole thing to get this one. And now we repeat this matrix multiplication, but I would take this one over here. All right, and now I have this one, I can probably copy because the real position is matched, copy it the same. So this is the way that I multiply just one by one. So say with G, so this is the equation G2, I actually means so G2 equals just from right to the left, G1 times M1, then times M2, then times M3, then times M4. I get this one. And so this is the result, kind of look like this, tilt it a little bit and scale. And now would like to repeat this. Just kind of bear in mind all the calculation we did, all the number to the right. This is not calculation. Every cell need to be calculated. Every cell here means there's a dot product somewhere. And then we have 4 relatively big matrix multiplication. Okay. And then now we want to see that what happens if we pre-multiply those transformation matrices. What I mean is that instead of multiplying directly, let's just remember, we just do this, pre-multiply this here, this. So this, okay. So this is pre-multiply this, and then I got just copy over here because the relative position is gonna give me the same. So if I recall, this is going to be M2, M1, this is going to be M3, M2, M1, this is going to be M4, M3, M2, M1 parentheses in this way. And then we do that, we have this joint kind of pre-multiply matrices. See what happens if we just multiply this thing. Multiply this resulting matrix to our input here. Oh, actually, Okay, I know I gonna need extra one, but I forgot to edit. But now I'm gonna edit. One. Okay, and now I'll get this result. If you check the number, I'm gonna roll out a little bit, so you can see the number is actually the same, exactly the same. And because then you look at the shape, that's exactly the same as well. All right, so this is all I have today. So we looked at the matrix multiplication a lot and how we can use matrix multiplication to perform transformation of a group of points. And then we looked at how we can scale it up to a batch of points instead of just one. For a batch of points, when it is kind of hard to compute by hand, we use the computer to do this, a matrix multiplication. And once you can see that, well, moving the group of points around really could be expressed in the matrix multiplication, you can understand the reason behind even having a graphical processing unit. A GPU was originally designed to perform matrix multiplication for 3D gaming. Why? Because you have a lot of points that need to be moved around in the 3D space in real time, where it's a really good frame rate for game to be fun. And then matrix multiplication was play a central role. Now you can understand why translating stuff more. Even though we look at 2D examples, this can be extended in 3D as well. So we'll look at it in the later part of the semester. When we look at stereo and camera model, we'll extend this example to 3D. And GPU will be found to support matrix multiplication for deep learning neural net as well, because when we look at deep learning, you will see a very, very similar structure as we're seeing today with a bunch of input and multiplied by weight matrices in multiple layers stack up in this way. Okay, all right. Thank you for listening. This is all I have today.